So now I'm going to talk about an example of duality in linear optimization. Actually, this example is the same that we used for simplex, the large example that was about a plant to manufacture 4 products, A, B, C, and D. So I skip the part that we try to formulate the problem based on the problem specification. I just write the primal problem here. The primal problem looks like this. Maximizing benefit, which was 5x1 plus 8x2 plus 4x3 plus 0.5x4, subject to x1 plus 2x2 plus 3x3 less than or equal to 12, 3x1 plus 2x2 plus x3 plus 2x4 less than or equal to 15, and 2x1 plus 3x2 plus x3 plus 3x4 less than or equal to 20, and all x1, x2, x3 and x4 are positive because they are quantities that represent the value of some real world product, so they cannot be negative. They can be 0, but they cannot be negative. So the first question is to write the dual problem. So this is maximization, so the dual problem will be minimization. We have B here. So B is going to appear in the objective function as coefficients. It will 12 y sub 1 plus 15 y sub 2 plus 20 y sub 3. So let's write down the A matrix here quickly. So A matrix of coefficient for the constraints is 1, 2, 3, 0, 1, 2, 3, 0, 3, 2, 1, 3, 2, 1, 2, 3, 2, 1, 2, and 2, 3, 1, 3. 2, 3, 1, 3. We find the A transpose. 1, 2, 3, 0, 3, 2, 1, 2, 2, 3, 1, 3. So this is a larger example, so you can see the change of structure that I was talking about. So we transition from A to A transpose. Now what we have to do, we have to multiply A transpose by the vector of y's, variables, y1, y2, y3, and then we also have C. C is equal to 584.5. So we use C transpose. At the other side of this constraint, it will be 584.5. So let's write down the constraints. The first constraint will be y1 plus 3y2 plus 2y3. And at the other side, we have 5. Okay, now the question is whether this constraint is equality, inequality, and if inequality, which type of inequality. So because x1 is greater than or equal to 0, so we have y1 plus greater than or equal to 5, 2y1 plus 2y2 plus 8y3 greater than or equal to 8. So this comes from this. 3y1 plus y2 plus y3 greater than or equal to 4, and 2y2 plus 3y3 greater than or equal to 0.5. And because all of these are inequality constraints, then all of y's are positive. y1, y2, y3 are positive. So we don't need this A transpose and A anymore. So we already did the first part of the problem. Then the second part of problem tells us to somehow solve each of these using the simplex method. So part B, solve both primal and dual problems using simplex algorithm. So we have to find the tableau and so on. But before doing that, we have to add a slack variables. Let's at least do it for the dual problem. So it's going to give me this new structure. I try to write it down directly here. So this is greater than or equal to something, so it should be minus the first slack variable, and then I can change this inequality to equality. I do the same for this. Minus S2 is equal to 8. Minus S3 is equal to 4. And minus S sub 4 is equal to 0.5. And we will have some new constraints. S1, S2, S sub 3, and S sub 4 are greater than or equal to 0. And the problem is already minimization. Variables will be y1, y2, y3, S1, S2, S3, and S4. Alright, if you solve this set of this constraint and objective using simplex, the answer will be y1 is 7 over 2, y2 is equal to 1 over 2, y3 is equal to 0, S1 0, S2 0, S3 7, and S4 1 over 2. Alright, so what this tells us, it tells us that these are the Lagrange multipliers for, let's call this constraint 1, and constraint 2, and constraint 3. Lagrange multiplier for constraint 1, Lagrange multiplier for constraint 2, Lagrange multiplier for constraint 3. So now the goal is to see what's the optimal value of the primal problem, optimal objective function value of primal. In order to do this, you simply need to replace these values in the objective function. So y1 is 7 over 2, y2 is 1 over 2, and y3 is 0. So it will be 12 multiplied by 7 over 2, so it's 6, 7, 42 plus 7.5. So it's 49.5. Okay, so you have the solution to your dual problem, and you know that this is equivalent to the value of objective function for the primal problem. What I want you to do at home is to solve the primal problem using simplest algorithm and see how your final tableau will look like, and try to extract some intuition to see how these two are related. So let's keep this part, which is the answer. at this point, what I want you to do is to please pause the video, spend a few minutes, and try to find the final tableau for the original problem. Now I'm going to write the original tableau, and you can compare whether what you have is similar to the tableau that I have here. Alright, so maybe the tableau that you have derived is not in the same order, because what we did, we bring all of these unit metrics here. We wanted to have 1, 1, 1 and all zeros here. But please switch the columns so you can make sure you have this order: x5, 6, 7, x1, 2, 3, 4. So if you do that and you try to compare this with the answers that we have the primal, so what it tells us, actually these were the solutions for x7, x1 and x2, right? But interestingly, you can see your dual variables. You can see y1, y2 and y3 here. So this is some sort of intuition for us, because it tells us how to find the Lagrange multipliers in linear programming. Also, if you look at the value of objective function here, this is the same as the primal. Yeah, that's all for today. Thank you.